Good morning, everyone, and thank you for hosting me. My name is Oded. I am the CEO and co-founder of Quantum Source. And in my presentation, I will provide you a short overview about what we do at Quantum Source, the technology that we develop, a technology that combines photonic qubits and atomic qubits and resolves one of the key bottlenecks of photonic quantum computation. But before I start, the opportunity behind quantum computing is huge. It is estimated that quantum computing can contribute more than $1 trillion to the world economy, creating huge transformations in areas like financial services, machine learning, cybersecurity, energy, climate, and so on. However, to unlock this huge potential of quantum computing, we need different machines. We need quantum computers which are large scale and fault tolerant. And by large scale, I mean quantum computers with millions of qubits. And why do we need millions of qubits? Because of error correction. Qubits are analog and are noisy. And in order to run algorithms which have significant market value, we need the logical qubits or the qubits to be with error rate of about 10 to minus 15 or even better. To achieve that type of error rate, we need to encode the logical qubits using between 1,000 to 10,000 physical qubits, just for one logical qubit with that type of error rate. So that means that we are looking at machines with the size of millions of physical qubits. Now, let's take a quick look at a couple of examples. To break RSA, we need roughly 6,000 so-called perfect qubits. That translates to several tens of millions of physical qubits. To run molecule simulation, and of course it depends on the specific molecule, we need roughly 10,000 or 1,000 so-called perfect qubits. That translates to few millions of physical qubits. So the gap between where the industry is today to where we need to be is still very big. Now, let's take a quick look at the leading technologies or the leading modalities to create quantum computing. On the left side, we see the matter-based qubits, superconductors, trapped ions, cold atoms. With those type of machines, it's relatively easy to create the qubits and to create the entangling gates. So building small quantum computers based on those type of modalities is a problem that already been solved. However, scaling up those systems to the millions of qubits is still an issue that's unresolved. With the photonic qubits, however, the problem is the opposite. Let me go back one slide. With the photonic qubits, scaling up, it's not the issue. So scaling up with photonic approach is relatively easy. However, generating the basic building blocks, the qubits and the entangling gates is very, very difficult. So what we do at Quantum Source, we combine the best of both worlds. We combine photonic qubits and atomic qubits. Photonic qubits for their ability to scale up, for their immunity to noise, and atomic qubits for their ability to entangle very efficiently. But before I will go in more details to what we do at Quantum Source, I would like to give you an overview about the general architecture of photonic quantum computation. So first, what we are trying to build. So what we see in this visualization is a large array of quantum logic. Each glowing point represents the qubits, and the lines between the points represent the entanglement. This is the scale that we need to achieve. Millions of qubits that are working together. The issue is how to generate this large array. We can try and create it using a huge machine, which of course is not available using current technologies, but we can also try to create it using smaller patches and combine them together. This effort of combining small patches or small arrays to a large array is an effort that many companies using many modalities are trying to address. And with Photonic, it's relatively simple. However, we can use even a more sophisticated, efficient method. We can try and create this large array of qubits, not just by combining smaller arrays in space, but combining those small arrays in time. Build smaller array and stack them up over time. This method, this strategy is only possible using the photonic approach, and we will see later on how that is possible. Now, let's go at and describe the key components of photonic quantum computation. So first, we have a machine called RSG, or Resource State Generator. It's a machine that generates repeatedly small clusters of entangled photons. Those clusters and then go to stitchers that takes the small clusters that were generated and stitch them together to create a larger array. But between the RSGs and the stitchers, we can also put fibers. And the fibers allows us to entangle photons that were generated in time X to photons that were generated in time Y. And by that, create this time multiplexing that I described. The output of the stitcher then goes to single photon detectors, and from there to classical computer that controls everything. So when we put all those elements together, we can create those arrays that I described in space and stack them up over time. This modular time-based approach is unique to photonic quantum computation, and it allows us to scale up the system very easily. So to summarize this part, the general architecture, with photonic quantum computation, we can build a computation as large as required, either by expanding the two-dimensional space by adding more RSGs, or by adding more time multiplexing, which means longer fibers. And of course, there is a trade-off here. The key issue with photonic quantum computation, however, is those RSGs, those machines that generates those small clusters of entangled photons. Building a 1 million qubit system, which is an effort that the industry is going after right now, will cost between $500 to $1 billion. 95 to 99% of the bill of material of such a huge machine resides here in the RSGs. And why RSGs are so complex and why they are so expensive? Because they use probabilistic processes to generate the qubits, and they use probabilistic processes to generate the entanglement between the qubits. And this is why a 1 million qubit system will probably occupy the space of a football court or even larger. And this is where quantum source technology is coming to play. We found a way to create those cluster states in a deterministic way and not probabilistic way. We use photonic qubits and atomic qubits. Again, photonic qubits for their ability to scale up, for their immunity to noise, and atomic qubits for their entangling capabilities. But photons are tiny units of energy, and atoms are like tiny antennas. How can we create deterministic interaction between one photon and one atom. The way to do it is by confining the photon in high quality, tiny resonator so that the electrical field increases dramatically for a period of time which is enough to create deterministic interaction with the atom. So that's the general scheme of the system. This area in science called cavity QAD, or cavity quantum electrodynamics, and it is the basis for all the things that we do at Quantum Source. And we use this technology to do two major things. One is to create single photons in a deterministic fashion, and also create deterministic entanglement process between photons in the system. In our system, and by the way, you're all welcome to see this system which is held by Professor Dayan out there. In our system, we trap very few atoms on a silicon photonic chip. And by using this process, which I will explain in more details in a minute, we can get a system which is about 4 orders of magnitude more efficient compared to the more conventional approach to generating the single photons and the entanglement. So these 4 orders of magnitude is extremely important because it means that the system can be much cheaper, smaller. We can actually build a 1 million qubit system in the standard server room. And more than that, this system works in room temperature. So it does not need any cryogenic environment, which further reduces the complexity associated with building such a system. So if you remember one of my first slides, maybe even 1 million qubit is not going to be enough. Maybe we need systems with 10 million or even hundreds of millions of qubits. With that type of approach, that is going to be possible. So now let's take a closer look at our system. So the core of our system is a small vacuum cell in which a rubidium atom, a cloud of rubidium atom, is held by external laser beam. And then a narrow laser beam is transferring very slowly rubidium atoms to the silicon photonic chip, which is located on top of the vacuum cell. And those rubidium atoms are trapped in designated sites near the high quality resonator. Now, if we take a closer look at the chip has 2 parts. The first part is a part which is responsible to generate the single photons, the qubits. And we are doing it in a deterministic fashion. And how that is done? We are trapping the rubidium atom about 100 nanometer from the surface of the chip. The rubidium atom is very close proximity to the high quality resonator. And then external laser beam excite the atom and create a repeated excitation to the atom. And from there, the photons are extracted to the resonator, and from there to the external waveguide. So we have a way to deterministically generate single photons on demand. Push button, we have a single photon. The second part of the chip is responsible for the entanglement. In this part of the chip, we have a second resonator and a second atom. And this atom is responsible to create the entanglement between the inputs of the photons. It is controlled by another laser beam to perform one out of a small set of photon-atom quantum gates. And the output is the desired cluster state. So we can think about this atom like a needle in the sewing machine. It creates entanglement between the photons. And it's important to understand that the atoms in the system do not interact with each other. They are independent. One atom is responsible for generating the single photons, and one atom is responsible to create the entanglement. So Quantum Source was established 3.5 years ago after about a decade of research in the Weizmann Institute of Science. We raised so far $77 million from top-tier VCs. We have 57 employees, about 25 out of the employees with a PhD degree. 6 professors are supporting the activity in various domains, including cold atoms, error correction, silicon photonic technologies, and many others. So I hope that now you understand my earlier message about leveraging the best of both worlds. We are the only company in the world that combines photonic qubits and atomic qubits on one platform. And we believe that this approach is super efficient and enables us to scale up quantum computers to the level that we need. So to summarize, large-scale fault tolerant are necessary if we want quantum computing to really change our world. We believe that the photonic approach is one of the most promising, if not the most promising approach to achieve the scale that we need. And within the photonic approach, we have a solution which is 4 orders of magnitude better efficiency because of the deterministic generation of the qubits and the entanglement process. And we believe that this approach enables us to provide systems at the cost and the size which will make quantum computing usable by corporates and governments. So thank you very much. Arigatou gozaimasu.